Jen taking over. Our next topic is statistical process control. There will be three of us that will be unraveling this whole concept. First being me, of course, followed by my teammate Luna and Angel. So, first let's define quality control. Quality control is a set of activities we perform to meet the quality of conformance. The term quality of conformance is the characteristics or standards that are set beforehand and serve as the guideline to upcoming outputs, products, and even the overall process itself. Statistical control is a method of quality control where we use statistical procedures to determine if a product or the overall process of our production is within an acceptable range or quote unquote within control. That means that any variation within the product output or the process of making the product itself is predictable and has irrelevant effect on the overall quality of the output. By irrelevant, I mean that while it does not perfectly fit the mold to what we consider as standard, it is still within range to what we deem as acceptable. So, the SCP answers two questions. One is, are the variations random or is the process stable? And the second being, is the inherent variability within an acceptable range? These questions will be hinted at as a this these questions will be hinted as these questions will be hinted as these question these question these these questions will be hinted at as we go further into this topic. Now, even though let's say a system is made to mass produce identical products, it is only natural for us to think na, since they are identical, then they must be the same in every way. But that is not always the case. There will always be some sort of variation between those outputs. Let's say you have two cookies. When you compare them together, they look practically the same. They even have the same amount of toppings between the two. Not to mention, even the placement is oddly the same or identical. But if you were to inspect it further, like let's say you put it under a weighting scale, you'll notice that there's a slight variation between the two in terms of mass. Let's say this has 50 grams of whatever it was made of, while this has only 48. We call that difference variation. But it doesn't always mean that those that have variation should be disposed of or eliminated just because it doesn't perfectly fit the quality of conference. A product or process could be deemed as fine if it is within an acceptable range, which means that the variation is small or irrelevant enough to not cause any problems. Speaking of variations, we have two variations. The first one being random or chance variation. These are variations that is considered natural or inherent, meaning that the cause of these variations are built in, therefore it is unavoidable and predictable. It is considered random if the placement of the characteristic that makes this output different from this one is completely different. And the same could be said for others. This is caused by several minor factors of the production, none of which is bothersome enough to cause a major problem, so you could not directly tell where it is coming from. But you could predict the likelihood of it happening. Because of this, it is unadvisable to perform immediate corrective action because doing so would mean that you had to change everything and would even lead to further unpredictability. Not to mention, it is costly. Usually, older machines have a higher chance to perform random variation, unlike newer ones. The second kind of variability is assignable variation or otherwise known as non-random variation. It can also be called special variation sometimes. This variation is when the variable trait of this product and this product is identical. Because of this, you know that the cause of this variation is specific and usually it is advised to be eliminated immediately since it is only one factor. This is considered unstable or unpredictable because it is not built in the system, so you cannot expect for it to happen. Next is the sampling procedure. We do this to find the variability of a product. So the first step is instead of inspecting every item, we take small groups, also known as periodic samples, of the output. The second is for each group, we calculate a single numerical value, such as the sample mean or the average size. This calculated value is the sample statistic. This sample statistic always show variability. They change slightly from sample to sample due to normal and random chance. For the third step, we use the sampling distribution. This is a mathematical pattern that describes the expected random variability of these sample statistics. We use this to understand how spread out this change should be. The pattern that we talk of is most often the normal distribution, the bell curve, which allows us to precisely calculate the control limits that define the range of acceptable random variability. There are two types of distribution. First, as we know, is sampling distribution. This is where we smooth out our sample means by finding the average out of each group rather than its individual values. By doing this, the graph that it will form will always be narrower than the process distribution. The narrowness of this distribution can be attributed to the sample size. The bigger it is, the narrower it gets. The process distribution has almost the same qualities as the sample distribution, with the exception that it isn't smoothed out. In other words, the values of the groups and its individual components stays as is. This is not meant to have a fixed appearance. It could be droopy and uncontrollable looking because this looks at everything as a full picture. The narrowness of this figure relies on the inherent capability of its components. Inherent capability is measured by comparing the process stable variation to the required specification limits. If the inherent variation is narrower than the required tolerance, the process has a high inherent capability. If the variation is wider, the inherent capability is low, meaning the system is designed to produce defects. Note that the narrower a graph is, the closer it is to its natural values, meaning it is more likely to be in an acceptable range or meets the qualifications of the cormorants. Control limits are established to tell the difference between expected normal fluctuations and major unidentifiable problems. These limits are determined by calculating a specific distance measured in standard deviation, defining an acceptable zone for normal variation. Practically, limits are generally set at three standard deviations, as this range reliably includes about 99.7% of all typical values, thereby separating normal variation from abnormal deviations. The resulting decision rule is simple. If a sample's average falls outside these limits, it signals a non-random event, and corrective action must be taken. Sampling and corrective action are only a part of the control process. Effective control requires the following steps. First is define, specify the exact characteristics to be controlled. This is followed by measure, which tells you to determine how the characteristics will be quantified. And of course, you will have to compare what you have qualified. Establish a standard, target value, and specification limits to judge the measurement against, followed by evaluation, which tells you to define out of control by distinguishing random variation from non-random variation. The fifth step is correct. Take action to uncover the cause of the non-random variability and fix it. And finally, monitor results. Follow up for a sufficient period to ensure the corrective action was effective. So, a control chart is a graph that is specially made by a guy named Walter Stewart. It's a plot for our sample statistics, shaped in a time order, so we track it day by day, hour by hour. The goal of this is to monitor these stats to make sure any variation we see is only random variation. We want our process output to be perfectly random and stable, so we can predict future output. If it's random now, it will likely be random tomorrow. The chart is built on the idea of a sampling distribution, which is the theoretical way random variability should behave. The most important lines are the control limits, the upper control limit and the lower control limit. These lines define our range of acceptable random variation. So control limits have one crucial and significant flaw, and that is that it cannot 100% capture the process variation. A small probability area still remains in the tails, and this causes two risks, which is the alpha risk and the beta risk, also known as type 1 error and type 2 error. So with type 1 error, this is a mistake of concluding a problem as non-random when only normal randomness is actually occurring. While type 2 error is when you conclude that process as in control or randomness when it's actually out of control. That means it's actually non-random. This happens when you incorrectly assume non-random variations are not present, but they are. Now handing this slide to my partner Luna.